Okay, hello everybody. Welcome to C++20 Ranges in Practice. My name's Tristan. I'll be your host for this evening. Um, let's begin our journey. So our journey begins, as so many good journeys do, a long time ago in a galaxy far, far away. Or, well, okay, last September in Colorado. So last September in Colorado, I was at CppCon 2019. I was speaking. There is me on stage. No, I really did it. And I gave a talk that was called An Overview of Standard Ranges. The YouTube link is there. That's mostly for when these slides go out later, but you can find it. You just have to search for that title on YouTube. And as the title suggests, this was sort of a broad brush overview of the new features that we're going to be getting in C++20. And, you know, it went pretty well, I think. And afterwards, I was kind of inundated with people asking me questions about things that I hadn't been able to cover in the time available in that talk. So this year for CppCon, I proposed a follow-up, and that follow-up is what you're watching right now. So if you haven't seen the overview talk, don't worry. If you've got some experience with ranges, if you've been using range v3, if you've seen a few examples online, you should be able to follow along today. If not, if you're watching this at some point in the future, then this overview talk is a good place to start if you have no experience with ranges whatsoever. So with that out of the way, what's on the menu for today? So today we're going to be looking at three programming problems, the kind of things that might turn up in a interview, the dreaded whiteboard thing. Reasonably simple problems, I think, but they're going to lead us down some interesting rabbit holes. We're going to try and use ranges to solve them. We're going to see, where that takes us, and hopefully, everybody will come out of this learning something. So, as I say, we're going to look at three problems. First problem, we're going to look at how to find the least element of an array. Now, you're probably sitting there thinking, well, I know how to do this. This is silly. Stick with it. As I say, we're going down rabbit holes today. Second problem we're going to look at how to calculate the sum of the squares of some numbers in an array. And then we're going to finish on my favorite problem, which is string trimming, and we're going to look at how we can use range adapters to do that, which I think is really, really cool, and I'm really looking forward to it. So I'll take questions at the end. Ideally, if I was doing this as an in-person talk, I would take questions as we go along. I think with the online format, because I'm on a bit of a delay, it'll work better if we leave questions till the end. Please do write questions in the little Q&A tab on Remo. Upvote questions if you think they're good questions. All being well, as long as I don't run over too far, we'll have some time left at the end. And the other thing to note is that every slide, you can see it just which direction over there. In the bottom right, we have a slide number. So if there's something on a particular slide that's perplexing you, if I've made any typos or silly mistakes or anything else, just take a note of the slide number and then we can go back to it at the end. So with that out of the way, let's crack on with our first problem for the day, which is calculating the minimum element of an array. So here's the problem statement. Given a non-empty array of integers, find the minimum value that it contains. So for example, if we're given an array of numbers 5, 22, 88, minus 12, and 14, we want to find minus 12. That is the lowest value in this array. Pretty straightforward. We want to find the minimum value in the array. Minimum value, minimum element, min element. There we go. So, of course, you could do this with a for loop in a few lines, but the existing STL comes with a function that will calculate this for us, and it's called standard min elements. So here is how you would, or you might find the minimum element in C++17. So we're getting our input vector, and then we're calling standard min elements with the beginning and end iterators from this vector. So pretty familiar stuff, I hope. And of course, we're getting new algorithms in the ranges namespace, rangified versions of these algorithms. So we can replace standard min with standard ranges min. Just a note that on these slides, I will quite often drop the STD just for space on the slides. You can just imagine there are using directives in place. So, and the other thing to mention is that everything I'm going to show today, except where noted, is part of C++20 ranges and is available today in libstandard C++ in GCC version 10, libstandard C++ implements the ranges stuff, and also MSVC doesn't quite have everything, but it's getting very close now. I think the latest preview version has quite a lot of support for ranges, so fingers crossed it won't be long before they have full implementation as well. So yes, we can replace standard min element with ranges min element, and of course we can still pass the beginning and end iterator if we want to, just as we could before. But min element is ranges algorithm, so we can pass the whole range if we want to. We can just pass vec, and this will in turn dispatch to the iterator version. So okay, yeah, that's pretty cool. That solved the problem. That was quick. Well, okay, so let's say you have something that looks a bit like this in your code base. Might not be exactly this, but something that looks similar. And one of the co-workers comes along and they're, weeks, months, years later, and they look at this and they go, well, hang on, I'm not actually using this this vec object after the call to min element. Why am I bothering saving it in a named variable? What's the point of that? Can't I just do this? Can't I just pass the result of the get input function straight into ranges min element? And when this comes up in code review, well, it should start setting off alarm bells, because we have a potential problem here. We have a potential dangling iterator, or at least we do on the face of it. So get input is going to return an R value vector, a temporary standard vector, and that vector is going to be passed to min element. Min element is going to do its thing. It's going to return an iterator into the vector. That's all fine. The problem comes at the end of the statement, or at the end of the full expression, if you want to be technical, at which point the temporary vector is destroyed. And then our nice iter variable there is going to be pointing into some deleted memory. This is bad. We don't want this. And this is not a problem that could occur in the old STL, because in that case, you always had to pass separate begin and end. So you always had to save the vector, in this case, as a variable in order to be able to call both begin and end on it. So this is, in a sense, a problem that ranges introduces by taking containers as a whole. Or it would be. But in fact, the question mark is there for a reason, because in fact, this, as it turns out, is not a problem, because ranges does something really clever. And what happens in this situation is that when you pass an R value container into an algorithm like min element that returns an iterator, or would normally return an iterator, what ranges does is it changes the return type so that instead of returning an iterator, it returns an object of type ranges dangling. So if we pass an R value container, something like a vector, into an algorithm like min element, like find, like anything that returns an iterator, the iterator return type will be changed so that instead it returns one of these ranges dangling objects. So this line, this will compile. This is just fine. But I was a bit sneaky. Because I used auto on iter, the actual type that is going to be deduced here, the type that min element is going to return for this input, is going to be one of these ranges dangling objects. Now, ranges dangling is more or less just an empty struct. It has no operations defined on it. So constructing a dangling object is not the problem. The problem comes when we try to use a dangling object. Attempting to use a dangling will cause a compile error. So if we were to do something like this, if we were attempt to dereference the iterator and print the value, we're going to get an error that looks like this. In fact, not just looks like this, this is the exact error that GCC prints out for this example. So no match for operator star, operand type is standard ranges dangling. And this is really cool because the error message has this name in it, standard ranges dangling. It helps you diagnose exactly what the problem is. If we see ranges dangling in an error message, we can look at it and go, okay, we are trying to use an iterator that we've got from an algorithm, and we've erroneously passed an R-value container into this algorithm. So we know what the problem is, and we know probably the easiest solution is just to save the input into a named variable so that we pass it as an L value instead. So, I mean, this is C++. We can't protect you from every use of dangling iterators, unfortunately, not until we get full lifetime checking and borrow checking and all of that stuff, if that ever happens. But this is something that, this is one particular case where ranges can help prevent errors, lifetime errors, and I think this is pretty nice. So ranges applies this dangling protection, as I say, whenever you have an algorithm that would return an iterator, ranges applies this dangling protection, transforms the return type into something involving this dangling type, something that's going to show up noisily in your errors. However, there are some types whose iterators can safely outlive their parent. For example, a standard string view, or new in C++20 standard span. So if you think about what a string view is, a string view just points into some other character array. A string view's iterators, in fact, just point into the other character array. So if you have a string view iterator, you can continue using that iterator after the string view itself is destroyed. As long as the underlying character array is still around, you can do things like this. This is kind of weird, but it's not problematic. This is safe. So here you see on the, what is it, the third line, we're creating a temporary string view, calling begin on it, and then the string view is immediately destroyed, but we can safely dereference the iterator. So types like these, like string view, like span, these are types for which we don't need the dangling protection that ranges offers. Because their iterators can safely dangle, they're not really dangling because it's safe, we don't need the dangling protection. So we can in fact disable it for these kind of types. And we do that by specializing a trait in the ranges library called enable borrowed range. In effect, we're telling the ranges machinery, hey, don't worry about it. These iterators can safely outlive their parent. So we specialize a trait like this. So this is an imaginary string ref type that you might have. It's quite common in code bases. So if we have one of these types, we can specialize the standard ranges enable borrowed range trait like this. It's a variable template. So we're just specializing variable template. So now if we use an algorithm like find, and we imagine that get string ref returns us an R value string ref, we've told the ranges machinery, hey, this is fine. This isn't going to dangle. So this is going to return you an iterator, not a dangling. So if we called find on get vector, it would return us a dangling. But we've told the machinery, ranges machinery, hey, string ref is fine. So it's going to give us an iterator back. So these kind of types, as we just seen, are called borrowed ranges in the ranges world. A type whose iterators can safely outlive the thing that you call begin on are called borrowed ranges. So there are two kinds of borrowed ranges, either L values. So again, if we pass an L value vector into find, that's absolutely fine. We're going to get an iterator out. So either an L value range or an R value range with this specialized trait, something like a string view or a span. So If we pass a borrowed range in, we get an iterator out. If we pass a non-borrowed range in, that's an R value which doesn't have the trait specialized, we're going to get a dangling object out of our algorithms. So this is a way, as I say, in which ranges helps protect you from making mistakes. So let's delve further into this rabbit hole and talk about views. So informally, when people are sort of talking casually, trying to explain in one sentence what is a view, sometimes people say, well, a view is a range that doesn't own its elements. And that makes it sound quite a lot like a borrowed range. They're actually distinct concepts. Because there are, in fact, views which do own their elements. There's one in the standard library, it's called single view. So more formally, a view is a range which is default constructible, has constant time move and destruction operations, and if it's copyable, has constant time copy operations. So views in the ranges world need not be copyable. They can be move only. It's pretty rare, but it's permissible. But these are the properties, formal properties that a view needs. And by constant time here, we mean independent of the number of elements in that range in the view. And what these properties mean is that we can pass views around by value within our range implementations without worrying about the cost of these too much about the cost of these operations, and without worrying about the algorithmic complexity multiplying and ending up with quadratic behavior and all sorts of bad things. So unfortunately, the compiler cannot work out for us whether copy constructors, assignment operators, etc., whether they have constant time complexity or not, right? Kind of beyond the ability of compilers to do. So we have to opt in to being a view, just as we have to opt into being a borrowed range, we have to opt into being a view. And just as with borrowed range, there is a trait enable view that we can use to do this. Or there's an alternative way, because view, there are no views, so people are going to be writing new ones. There's a base class, an empty base class called ranges view base that we can use to do that. Or there's another base class called ranges view interface, which is actually more useful and which gives you a load of default operations that we can use to mark a particular class as being a view from the point of view of the ranges machinery. So if I had longer time available, if this were a 2-hour talk, I would love to show you an example of how you would write a view, how you can use the view interface base class. Fortunately, don't have the time available, but maybe I'll do another follow-up next year, who knows. So as I mentioned, views and borrowed ranges are distinct concepts. There are views that are not borrowed ranges, there are borrowed ranges that are not views. But whenever we have a borrowed range, we can convert it into a view using this function views all. That is the purpose of this views all function. So views all takes a borrowed range. Remember, that's either an L value range or something like a span or a string view. And it returns you a view object. So here's an example. We've got an L value vector. We're passing it into views all, and we're getting out some view object. This is in fact going to be a ref view. I mean, you don't really have to care, but it's going to be a ref view. It's a tiny object. It's literally a wrapper around a pointer. So this is incredibly cheap to pass around, to copy, etc. So together, views and borrowed ranges are collectively called viewable ranges. That is, they are things that can be turned into views. Why does this matter? Why have I delved so deep into this ranges minutia? Well, here's the most important sentence of this little section. Range adapters only operate on viewable ranges. So in order to use a range adapter, you need to have either another view or you need to have a borrowed range, that is an L value container or one of these things that has specialized the borrowed range trait. So as I said, after I gave the last talk, I got lots of questions from people, and a lot of people got very confused about why they were passing an R value vector, say, into a pipeline, and they were getting cryptic error messages out. Why wasn't this working? Well, it's because range adapters only operate on viewable ranges, views or borrowed ranges. So let's just show you what I mean by this. So we've got our L value vector called vec, and here it's an L value. It's got a name, it's an L value. So I can just pipe that into views transform, and this is going to work just fine. Vec is an L value, therefore it's a borrowed range, therefore it's viewable, therefore I can use it with views transform. Second example, we've got an imaginary function called getSpan. Imagine it returns us an R value span. Well, a span, standard span, is a borrowed range. It's also usually a view, not always. Let's not get into that. But it's a borrowed range, so it's viewable, so it can be used as an R value with views transform. That's going to work just fine. Subrange is a new type we're getting in the ranges library. It's basically a wrapper around, just holds an iterator and a sentinel. So it's a very lightweight object, kind of like a span, but for ranges that are not necessarily contiguous. So we can construct a subrange, just an R value subrange, and we can pass that into views transform because subrange is borrowed and it happens to be a view as well. However, what we can't do is this last example. We can't have get vector, which returns us an R value, our PR value, in fact, vector. We cannot pass that straight into the views transform because get vector returns us an R value vector, and that's neither a view nor is it a borrowed range. Vector does not have this trait specialized because its iterators cannot safely dangle. So most of the time, people try and do something like this last example. They get, unfortunately, really cryptic error messages. Hopefully, we're getting better at that. Hopefully, as these things mature, we'll get, compiler error messages will get better using real concepts and so forth. But you cannot do this last thing. And the reason for that is that the transform view actually has to store the thing it's called on inside it. And if it stored a vector inside it, well, then its destruction operation, its copy operation, would then have to call the equivalent operations on the vector, and they'd no longer be constant time. So it would violate the requirements of the view concept. So you can't do this last one. What you have to do is, in fact, save the vector in a named variable and pass that into the algorithm, the adapter. So we started off just looking at getting the minimum elements. It turns out we solved that on slide 1, but it helped us get down this rabbit hole of looking at borrowed ranges and views. I did write a blog post on this as well, if you're somebody who likes reading things and having a bit of a reference. I haven't put a link to it on the slides. I probably will before they're put up. But if you go to my website, tristanbrindle.com, there is a blog post on this where I go into a bit more detail than I've been able to today. So that's part 1. Let's go. I'm going to have a quick sip of water, and then we'll go on to look at problem number 2. So our second problem. Given an array of integers, calculate the sum of the squares of the values it contains. So, for example, if we're given an array containing -2, -1, 0, 1, 2, the squares are 4, 1, 0, 1, 4, add them up, and hopefully you get 10. So how can we do this with the existing STL? Well, various ways, of course. There are always multiple ways of doing this, but one way we might do is by using standard transform followed by standard accumulate. So transform, we're going to transform from the beginning of the vector to the end. We're going to put the results back in the beginning of the vector. We're going to apply this square function to every element. So we're going to transform the vector in place, replace every element with its square, and then we're going to use accumulate to sum up the values that we have. So again, pretty straightforward, and we can, of course, replace standard transform with standard ranges transform. We no longer need to say vec.begin and vec.end for the first vector. We do for the second because it takes an output iterator, but we can replace this with ranges transform, and this is going to do exactly the same thing. But we can immediately do quite a lot better. And that's by replacing the eager transform, ranges transform, with this lazy transform view instead. So this is a lazy operation. This only performs the transformation when we dereference the iterators, as we dereference the iterators as we're iterating over this range. So this is immediately better because previously we were doing 2 passes over the input range. Now once to transform and then once to accumulate. Now we're just doing 1 pass. So immediately this is pretty cool. And we can write it using the pipe syntax as well. So we're having vec, and then we're piping it through views transform with this square operation, and then we're piping it through views common. So just to explain what's happening there, it turns out in this specific case, we don't need views common. We can get away without it. But because accumulate is a C++17 era algorithm, it expects its begin and end values to have the same type, for them both to be iterators. But in the ranges world, we can have separate sentinel types. And this is going to confuse accumulate. So it's good practice if you're calling a C++17 era algorithm to on a transformed range, is to pop this views common adapter at the end. And what views common does is it transforms the range into one that has a common type for the iterator and sentinel. So it turns out that in this specific case, we wouldn't need it if we were just doing a transform. But if we were doing something more complicated, something like a filter, then we might need it. So views common does nothing if it's already, it's just a pass through if the range already has the same type. So there's no harm in popping it on the end. And it's good practice if we're passing something into C++17 era algorithm like this. So we've replaced standard transform with views transform. That's great. What can we do about accumulate? Well, unfortunately, C++20 doesn't have rangified versions of the algorithms from the numeric header. Remember, accumulate is in this other header, numeric, not in algorithm. I wish I knew why this split had occurred. Fingers crossed, we're going to have this in C++23. It turns out that the numeric algorithms are actually pretty difficult to specify the concepts for. That's why they're not in C++20. But work is underway. Christopher DeBella has a paper in progress. I believe the committee's looked at it once already to bring these to C++23. And I know C++23 is all up in the air, and I can't promise anything is going to be in there. But I'm really hopeful that we're going to get these numeric algorithms in C++23. So, being that we don't have a rangified accumulate, let's write one. So this is the rabbit hole that we're going down this time, right? Because I imagine a lot of you will have algorithms in your own code base that use these C++17 or older concepts. And the purpose of this is to kind of show you how you can modernize those to use C++20 ranges instead. Yes, okay, sort of tricked you with the sum of the squares. That was just a hook to get us into doing this. So let's begin with an implementation of accumulate as it starts out in C++17. So this is accumulate with the default plus operation. We're just going to update init every time, as we iterate over, add the new value to the existing value, and then finally return the value. So immediately, the first change we want to make, as I mentioned, C++20 ranges, we can support different iterator and sentinel types. So we're going to add a new template parameter S for the sentinel. And you can see the only thing we're doing with last is comparing it to first. That's the only thing sentinels are required to do. So we're all good. There are actually 2 overloads of accumulate in C++17 and older, one of which takes a user-defined operation and one of which defaults the operation. to plus. Well, we can combine both of those things. We can just have one version. What we're going to do is we're going to add the operation as a template parameter that's defaulted to using standard plus. And then as a function parameter, we're just going to, again, default construct the operation we were given. And then in the body of the loop, you can see we're using this operation. So if you call this function without the op argument, it's just going to do exactly what the old version did. So I mentioned that accumulate in particular is quite difficult to specify concepts for. It's again, this is a rabbit hole I don't want to go down. So we're not going to try and do that. That would take, you know, this entire video, I would imagine. So what we're going to do is we're going to use concepts just enough to be able to disambiguate the overloads of accumulate that we're going to write. If we were, you know, masochistic, we could use Sphene to do this. We're going to use concepts instead. So actually conceptifying your algorithms generally tends to be really, really difficult, in my experience at least. So just for the purposes of this example, we're not going to go all in. We're just going to use enough just to disambiguate the overloads that we're going to write. So these are the concepts we're going to introduce. So we now require that I is an input iterator and S is a sentinel for I. So we're using a requires clause here. Of course, we can put these in the template head instead. So we're saying that I is an input iterator, S is a sentinel for I. And apart from that, everything is as it was. Everything's hunky-dory. There's actually one more cool thing we can do. Standard accumulate, you always have to provide the initial value. Vec.begin, vec.end, 0. That's kind of a drag. I wish we didn't have to do that. So for our implementation, what we're going to do is we're going to provide a default for the init type. So we're going to use this alias iter value t, which is the value, as you might imagine, the value type of the iterator I. So we're going to default the template parameter. We're going to default the function parameter to just a default constructed init. So for our case, we're calling this on a vector of integers. The value type of the iterator is going to be an int. We're going to default construct an int that's 0. So we're going to get what we want. So let's have a look at what that does to our function, a little function we were writing. Well, this is what it looked like before, and we're going to replace this with our newly written range accumulate function. And well, okay, we've managed to drop the 0, but so far it doesn't look that different. The other thing we've been able to get rid of is views common. Because we now support separate sentinel, iterator and sentinel types, we no longer need common. So it's a little bit nicer, but there's a little way to go yet. The next thing we want to do is to be able to support passing ranges directly. So what we're going to do is we're going to add a second overload of accumulate. And this is what it looks like. So this is saying we're taking as template parameters an input range R, an initial value, which this time we defaulted to the range value type. That's the iter value type of the iterator type of the range, which again, in our case, is going to be int. And we're defaulting the operation to standard plus again. So we're going to, and in the body of accumulate, the range-based accumulate, all we're going to do is call begin and end on the range we were given, and we're going to forward to the iterator, the iter sentinel based version. And this is exactly what all of the range-based, the range-based algorithms do in C++20. All they do is just forward to the iterator sentinel versions. So this is, you know, perfectly inlineable by the compiler. This is really trivial for it to do. So we've now got two overloads of accumulate, one taking the iterator and sentinel that actually does the work, one that takes a range that just forwards to the other version, a convenience overload. So using this, we no longer have to call view.begin and view.end. We can just call range accumulate on our view. So, hey, this is now starting to look a bit nicer. In fact, we can go a bit further. we no longer have to save the view as a named variable. We can just pass it straight into accumulate, just like that. So, whether you find this more readable or not, I guess is a matter of preference. But we can do it now. So that's pretty nice. But it could be nicer still, because the ranges algorithms in C++20, most of them take an extra optional parameter called a projection. Now, I talked about projections in the overview talk last year, gave an example of what they do and how you use them. But a projection is basically like a transform that is built into the algorithm call itself. So they're really handy. I really love projections. I don't think they get enough love. So I'm going to add a projection to our version of accumulate. So here's what our iterator sentinel version looks like with a projection. So you can see I've added an extra template parameter, proj, and that's defaulted to this type std identity. So std identity is just a pass-through function. It does absolutely nothing. It just returns what you give it. So proj is defaulted to standard identity, but of course we can provide our own projection if we want. And then, so we're defaulting the template parameter, and again, we're defaulting the function parameter as well to just a default constructed whatever projection we're given. And then in the body of the loop, you can see instead of just passing star first into the operation, what we're first doing is invoking the projection on star first. So this is what projections do. They're like a transform built into the algorithm. So again, if we're just using identity, this is just going to be a pass through. It's completely transparent to the compiler. There's no overhead, but it allows us to use a projection if we want. I love projections. I think they're awesome. So we're also going to add one to our range accumulate. Just exactly the same. We're just going to default to using standard identity, the pass through, and we're going to default construct the proj argument to our function. So this, incidentally, is the reason that we just use this minimum amount of concept, is because these things take, both of these overloads take variable numbers of parameters. We need to be able to disambiguate them in a way that couldn't be done, well, you'd have to use sphen A and lots of horrible things to do in C++98. Now we can use concepts, and it's a lot of things, life is better. So again, in the body of this function, we're just going to forward the projection parameter onto our main overload of accumulate. So here's some square function as it was. We're calling it accumulate on this transformed vec. Well, now we can dispense with views transform. We can just use our projection directly. So we're going to call accumulate on the vector. We're going to default the initializer. It's just going to be an int of 0. I could have written 0 in there. We're going to default the comparator. Not the comparator, sorry, the binary operation. It's going to be standard plus. And then we're going to pass this lambda as our projection that's going to square every element. Right. I think this is cool. And of course, because accumulate doesn't return iterators, it just uses up the range. We're not returning any iterators into the range. We don't have to worry about lifetime issues, about dangling, about borrowed ranges. We can just replace this. We can just pass get input straight into our accumulate function. And so, yes, you could do this with transform reduce in the existing STL, but I think this is really cool. This is what we hopefully will be getting in C++23. So all being well, we will get rangified versions of accumulate and friends, adjacent difference, all the other algorithms in the numeric header. All being well, we'll get those in C++23. In the meantime, I have written some implementations of accumulate and friends that are compatible with C++20 ranges. You can find them at that GitHub link. They're there as a stopgap until we get the real thing in C++23. So I hope that was a useful example of how we can how you can go, if quite rapid fire example of how you can rangeify C++17 algorithms, how it can make the function, your function calls, I think, prettier, easy to use, more expressive, easier to read, more expressive. You know, I like it. So time is marching on. So without further ado, let's move on to our third problem for today, which is string trimming. This is my favorite. I've been looking forward to this one. So here's our problem statement this time around. So given an input string, we want to construct a new string with a leading and trailing white space removed. So if we have this string with a bunch of junk at the front, space, new line, tab, etc., at the front and at the rear, we want to get rid of it and just return hello world. Now, again, as with all these problems, there are tons of ways that you could do this. Obviously, we're going to be using ranges. And in particular for this problem, we're going to be using range adapters. So first of all, let's have a look at the function we want to write. We want to take, if we're given a string, we want to call, we have this function called trimstr, and we want to return a new string. I could have taken a string view, but you know, I'm being old school. So the way we're going to do this is we're going to break the problem into two. We're first of all going to write a trim function, which returns us a range adapter. Returns us, an adapted range, returns us a view. And then we're going to pass that view to a toString function, which is going to convert it into a string. So we're going to break the problem down into two parts. So first of all, let's look at toString. What does our toString function look like? So our toString function is going to accept any range. Again, I'm omitting concepts here just for brevity. If we were being really, you know, doing this in production or for something that was going to be used in a variety of situations, you'd want to use the concepts here. I'm just omitting them just for brevity, really. So how do we implement this toString function? Well, here is one way we could do it. So standard string has a constructor that accepts an iterator pair, but that expects a C++17 iterator pair, that is begin and end having the same type. So in order to use it, we need to, or possibly need to, pass the input range that we're given through views common. Again, just as we did before, if we are given a range that have differing iterator and sentinel types, this is going to sort that out for us and give us something that most of the time we can call the standard string constructor on. Obviously, goes on said, this also requires a range whose reference type is convertible to a char. This is, as I said, if we were doing concepts, that's on this function, that's what we would check. One of the things we would check. This function is going to, and you can adapt this function. You can imagine writing a very similar two-vector function. A function like this is going to do what you need 90-something% of the time. There are a few corner cases that this won't handle. A few types of iterators that even after passing them through views common, that aren't valid C++17 iterators. The most common is move-only iterators, which are a new thing in ranges. They're not very heavily used yet, but they wouldn't be handled by this. But as I say, 95% of the time, this is going to do the right thing. But we can do better. If we were using range v3, range v3 has an adapter called ranges2, so that you can do something like this. You can construct a complex pipeline, and at the end of it, you can put ranges2 standard string, and that will process the range, consume the range, and convert it into a standard string. So ranges2 is really awesome. Unfortunately, it was proposed for C++20, but unfortunately was just a bit too late in the process, so it didn't make it into C++20. It's another one of those things that I really hope is going to be in 23. It has been proposed. The proposal is still in flight. I really hope we're going to see it. It's really, really useful. It handles all the corner cases that this function doesn't. So can we use ranges too? Well, as I say, it's not in 20, but fortunately, Corentin Jabot, I hope I pronounced that right, who is the author of ranges 2 and various copious other standard library papers, has written a library he calls Ranges Next, which has an implementation of Ranges 2 that is compatible with C++20 ranges. So if you go to that link on GitHub, it's also got a few other things that we hope to see in 23 that are proposed. So this is a sort of ranges extension library that of things that will hopefully see the light of day in 23. So this is a really, really useful thing to know for things that you would like but aren't yet in C++ in the standard version, not in C++20. So rather than writing that toString function, we're not gonna bother with a function call. We're just gonna have our trim_str function, and we're gonna do what we said before. We're gonna, in a minute, write a trim function that returns us a view, and we're gonna pipe that view into Corentin's Ranges Next 2 implementation. And of course, we don't really need the intermediate variable there. We can just do it like this. Oh, sorry, that shouldn't be return view equals. That should just be return trim_str pipe thing. That's a bad copy and paste error. I apologize for that. So that's how we're going to do the string conversion. How are we going to write this range adapter? Well, let's have a go at it now. Let's start off with a function template, a template of a function, a template of a function template that looks like this. So we're going to have our trim. It's going to take an arbitrary range, and it's going to return something. Well, actually, again, we're going to break the problem down into two. We're going to write a trim front, which removes white space from the front of the string, and we're going to write a trim back that removes white space from the end. So the reason we're going to do that, it's not just because it makes it easier, but because trim front and trim back are useful operations in their own rights. So, and it kind of makes sense to do it this way. So we're going to take the range, we're going to pass it through this trim front adapter, we're going to pass the result of that through the trim back adapter, and then we're going to return that as the return value of trim. So next level, let's dive even deeper. Let's take a look at trim front. How do we write trim front? We want to trim white space characters from the front of our range. That is, we want to begin at the beginning of our range, look at each character in turn, say, is this white space? Okay, well, that's no longer the beginning of my range. The next one is that white space? Oh, it is. Okay, well, I'm now going to say that's the beginning of my range, and so on and so on. We want to drop elements from the front of our range whilst a condition is true. And yes, there is an adapter in C++20 that does this. It's called drop while. So what we can do is we can take our range and we can use the drop while adapter, and the isSpace function is not great, but for the purposes of slides, that's what I'm going to use. Just the isSpace function, which tells you if a char is a particular character is considered white space or not, according to C's rules anyway. So what trim front is going to do is it's going to return us an adapted range. It's going to take the range we give it. It's going to apply this lazy drop while adapter, and it's going to return us some specialization of drop while view. We don't really care. That's why the function returns auto. And I've written it using the function call syntax. I could equally have written it using the pipe syntax like this. The two are equivalent. So this is going to give us an adapted range that drops the white space from the front of our range. So we're halfway there. Yes. So now let's have a look at trim back. How do we implement trim back? Well, in the ideal world, what we would be able to do is we'd be able to do something like this. We'd be able to call views drop last while, which would go from the end. Do the same as drop while, but work from the back of the range. Unfortunately, drop last while doesn't exist. You can write it, and it's not all that hard to do. I have an implementation of it if anybody's really curious. But unfortunately, this doesn't exist in C++20. I doubt we'll see it in 23 anyway. And the reason for that is because it's possible to do this another way. If you think about what we want to do, we want to, whereas drop while goes from the beginning of the range, we want to do exactly the same thing, but work backwards from the end. So the way we can do that is by first reversing our range, then counting from the front, and then reversing the range again. So rather than using drop last while view that doesn't exist, we're going to take our range, we're going to reverse it, we're going to drop from what is now the front, and then we're going to reverse it again. So this is pretty cool, I think. This is building up an operation pipeline to trim from the back by reversing. Of course, this requires a bidirectional range. Again, if we were doing concepts, we'd take care of that. But a standard string view, almost any string type you use, is going to be bidirectional, so that's not going to be a problem. So let's put these things together and have a look at where we are with our trimming operations. So we've got trim front, uses drop while, trim back, which reverses, uses drop while, reverses. And then we've got trim, which combines the two operations. And then we've got this trimstra version, which just does this specially for standard strings, because that's what we were asked to write. So this is pretty good now. You know, I quite like this. This does what we were asked to. It's one page of code, and we've got these reusable trim back, and trim front operations that will work on any bidirectional range of char, more or less. So, you know, this is pretty good as it stands, but we can make it better. So let's, for the moment, focus back in on trim front again. So what does this do? This function takes an arbitrary range and it pipes it through drop while, and this returns us an adapted range, a lazy range. Well, actually, we don't really need to do all this work that we're doing, or at least not in this function. What we can do instead of taking an arbitrary range and piping it through drop while, is we can just return the drop while view itself. This is now, instead of returning an adapted range, we're now just returning the adapter. So we're not quite doing the same thing we were before. We're doing something slightly different, but as you can see, we're cleaning up the code a bit. Instead of returning an adapted range, we're just going to return the adapter that later on someone can use. And we can do the same thing with trim back. So here's trim back as it was, as a function template, taking an arbitrary range. And we can do the same thing. Instead of returning an adapted range, we're going to compose adapters to return a new adapter. Now, this is something that I don't think many people know really that you can do with ranges, but is really cool. Is reverse is just an adapter, drop while is just an adapter. But we can compose these things together, even without piping a range into them at the start. We can compose these things together to create a new adapter which is ready for use, which we can pipe a range into. So that's pretty cool. Helps us simplify our code, or does it? Well, if you think about what we have to do now, trim front is a function that returns an adapter. So in our trim function, things have gone a bit haywire. Things have gone a bit lispy. We've got lots of parens everywhere. So we're calling trim front, that's returning us an adapter, and then we're calling that adapter and passing it our adapted range. And then we're doing the same thing with trim back. So this is beginning to look a little bit nasty now. Fortunately, things begin to make a lot more sense if we use the pipe syntax instead. So now trim takes the range you give it, passes it through trim front, passes it through the adapter that trim front returns, passes that through the adapter that trim back returns, and gives you the adapted range, which we're then iterating over using ranges 2, converting it to a string. So instead of 3 function templates, we've now just got 2. In fact, we can apply exactly the same logic to trim itself. So trim, we can replace with something that just takes the return value of trim front, that takes an adapter, composes it with the adapter returned by trim back. And then in our trim str function, you could say we're calling trim first, that's giving us back an adapter, and then we're applying str to that adapter. Again, this looks kind of horrible if you look at it like this. It makes more sense if you use the pipe syntax instead. So this is like looking pretty nice now, I think. I like this. I think this is cool. But there's one more trick we can play. Well, trick. It's not a trick. There's one more awesome thing we can do to make this even nicer. So here's our function trim front that we were just looking at. And this now returns us the drop while adapter using isSpace. Well, this is a function that always returns the same thing. Returns us the views drop while function object. This call is going to return us a function object. So this function is always going to return return the same thing. What we can do is save it as an inline constexpa variable. So we no longer need the function call. This is awesome. So inline variables are a reasonably new thing. They just save you from potential ODR violations if you include the header and take the address and what have you. Constexpa doesn't, by the way, refer to the call operator here. It just refers to the constructor, and we can construct this at compile time, and that's all fine. So we can replace trim front instead of it being a function. It's now just a function object. And we can do the same thing with trim back. We can replace our function with just a function object that does the same thing. So trim back is reverse composed with drop while of isSpace composed with reverse. So we can do that for trim back, for trim front, for trim back, and of course we can do it for trim as well. And now we've reduced our code even further. And I think that this is absolutely amazing. I absolutely love this. So our trim string function, what it does, it takes the string, it pipes it through trim, and then it pipes that onto range next 2. And trim is composed of 2 adapters, and one of those is a specialization of a standard adapter. Another one is a composition of some standard adapters. I think this is absolutely awesome. I love this, and this is what makes me excited to work on ranges. So that's it for my talk. I have used up every moment of my allotted time. So thank you very much, everyone, for sticking along. I hope we've still got a couple of minutes left for questions. I'll maybe just take a couple of questions because I'm not quite sure how long we've got. Otherwise, I will be hanging around in the Remo lobby just in about 5 minutes or so. Come and find the table I'm sitting on, and I'll be happy to answer questions for as long as people keep asking them. So thank you very much. So just going to look at some questions now. Could you immediately dereference the dangling iterator to avoid the lifetime issue? So this is a good question. So if you say star ranges min element, you are correct in that if you did that, there would be no lifetime issue. However, min element doesn't know that you're immediately going to dereference it. So min element past an R value range is still going to return you a dangling. So that line, as written in the question, is going to generate a compile error that you saw before, no operator star in ranges dangling. Fortunately, and I didn't show it, but perhaps I should have done, there is a new overload of min, called ranges min, obviously, which basically does do the immediate dereference that you wanted to. So an even easier way to do, because in the question I guaranteed that the range was non-empty, we could have just used ranges min, but that wouldn't have allowed me to dive down this rabbit hole about borrowed ranges. A question. What is the point of returning ranges dangling instead of having static asserts that's allowing the call? Well, actually, for a short time during the ranges standardization process, these calls were made ill-formed. They were made hard errors. And the reason you don't want that is because it's generating the dangling iterator is not a problem. It's only a problem when you try to use it. So probably more algorithms than you realize return iterators. So standard copy, for example, standard sort, these return iterators. So standard sort is not very useful calling that on an R value, but standard copy, you can imagine copying an R value vector into an output string to print it. That would be really annoying if that was disallowed, because 99% of the time you don't really care about the return value of standard copy. So ranges dangling, rather than disallowing these things outright, it says, okay, what you've done is okay, provided you don't try to use what would be a dangling iterator. And the reason, and another suggestion, it's not in the question, but somebody said, okay, well, why is this dangling type? Why not just void? And the reason for that is, as I mentioned, ranges dangling is a nice, loud type that shows up in your error messages that tells you exactly what's gone wrong, whereas void would give you a lot more cryptic errors. So next question, I'm just going to continue until I'm told I can't anymore. So what's the performance impact of ranges versus the STL? So that's several questions in one that I will do my best to answer. So firstly, the performance impact of the ranges algorithms, that is the algorithms in the standard ranges namespace, standard ranges sort versus standard sort, there is no performance impact whatsoever. They are using the exact same code, almost certainly using the exact same code paths. They do a little extra template checking, constraint checking, and so forth, but the actual generated code is going to be the same. So there is no runtime performance impact of using the eager algorithms. In terms of using range adapters, it's one of those annoying answers in that it depends. As a sort of general rule that I'm very hesitant to say applies too widely, as a general rule, not just in C++, but using lazy evaluation is sometimes slower than doing eager evaluation. Now, having said that, we saw an example of where we reduced, instead of doing 2 passes through a range adapters let us just do a single pass through a range. So there are situations in which using range adapters can, conceptually, theoretically at least, it always depends, always measure, etc. There are situations in which using range adapters can improve the performance of your code. So the answer is, unfortunately, it depends. Okay, so my time is up. So thank you very much, everybody, for watching. Thank you very much for the questions. I'm sorry we didn't have time for many more. I will be hanging around on Remo for a while, so please do come and find me. And I will do my best to answer. So thank you very much, everybody. And oh yes, by the way, these are some links that were mentioned if you missed them as we were going through. Thank you.